Okay, some hints for homework set 10. 4.43.1 has you basically establish U substitution in a certain setting for integrals involving complex numbers. We're taking W of t as a contour, WT as an integrand, written as U of t plus IV of t, so we've got its real and imaginary parts. You're asked to show if you integrate from a to b, W of t dt, that's equivalent to integrating from alpha to beta of W of phi of tau, phi prime of tau, d tau, where we're doing a change of variables from t to tau. So t is a function of tau. That function of tau has a positive derivative, tells you certain things about the endpoints. And let's see, phi of tau is a real valued function with a continuous derivative. Okay, it's the whole statement in terms of hypotheses. So, by the way, that phi prime is continuous gives you that the integrand is still a continuous function. So this is just basically, it's U substitution, or phi substitution, or tau substitution if you like. So what we'll do is make the substitution, t equals phi of tau. Okay, we'll pick up then a phi of tau there. We'll calculate the differential, t equals phi of tau implies dt equals phi prime of tau, d tau, definition of differentials. But this substitution stuff, that's only good in the real setting. So you better be in the real setting. Well, I guess it's true in the complex setting too, because that's what you're proving. But don't just use an immediate assumption that you're good to go with U substitution in the complex setting. That's actually what you're proving. So you'll take this integral, you'll bust it into real and imaginary parts and use this substitution on those parts where you know it's good from calculus 1 in the real setting. And you've got W expressed in terms of real and imaginary parts. Phi itself is purely real valued, so I think you're good to go to bust it into real and imaginary parts. Apply tau substitution to those parts and then glue them back together, and that'll give the result. Number 46.7 says, integrate about C, I think C is half a unit circle in number 46, quarter of a unit circle. So you're integrating around, looks like theta ranges from 0 to pi halves, and we'll take an e to the I theta. It's the quarter of the unit circle in the first quadrant. And you're integrating z to the negative 1 minus 2i. The principal branch of that function. Being a complex number to a complex power, it's defined in terms of exponentials and logarithms. If it's defined in terms of logarithms, there's concern over all that branch stuff. So we're using the principal branch of the logarithm to define the principal branch of this particular function, and principal branch of the logarithm has a branch cut along the negative real axis, and that contour won't intersect the negative real axis. So you'll be good to go. My hint is, hey, you can find an antiderivative of this. Do not add 1 to the exponent and divide by what you get. You don't know that stuff. It's all tied in with this branch stuff. Break it into functions that you recognize. It'll be exponential functions. You'll see some e to the I theta or something like that in terms of the integrand. And this will simplify down to an integrand that has an antiderivative. That we're good to go on. You can find an antiderivative of this. We're good to go in terms of evaluating the integral from there. So take principal branch definition, expand this out in terms of exponentials and logs, some things will cancel. You'll end up with an exponential of this form or similar to this form, and that you're good to go to integrate with antiderivatives. Number 46.11 says integrate z conjugate over this contour here, so it's half of a circle of radius 2. They've described it, parameterized it in terms of y, and calling the contour z of y. They're taking z of y to be the square root of 4 minus y squared plus I times y. Okay, so we're going to have some problems with z prime of y at the endpoints. They parameterize this for y equals negative 2 to 2. So y equals negative 2 to 2, and they've expressed the z in terms of y. But we're going to have some problems at the endpoints. You don't have problems with the contour at the endpoints, but somewhere in there there'll be a dz term. That dz term will be related to z prime of y dy. Z prime of y, you got a problem at 2 and negative 2. You got a problem of division by 0 at the endpoints. And the only way to deal with that is taking that integral from negative 2 to 2 of whatever, squiggle dy, and writing it as a limit from a to b of squiggle dy, taking a limit as a approaches 2 from the positive side, and a limit as b approaches, oops, they're both approaching positive. I need that lower one to approach negative 2. Negative 2 from the positive side, and positive 2 from the negative side. So what we're really doing geometrically is you're evaluating integrals, and then you're taking little limits as the bounds approach the edges. And that's how you deal with the fact that the integrand will have a vertical asymptote at those endpoints. But write it in terms of limits, and then you're good to go. Number 46.13, I gave 3 stars and a smiley emoji. Has you compute around c sub 0, which I trust is probably just a circle, about 0. But c sub 0 denote the circle centered at z sub 0 with radius r. Now, centered at z sub 0. So this is a contour, simple closed contour that goes around the point z sub 0. All right, I'm worried about division by 0 in this function. When n equals 0, we've got 1 over z minus z sub 0. And when you see those 1 over z type functions, integrals are going to involve branches of the logarithms, and here comes trouble. Just compute the two cases. If you let n equal 0, you have the equipment to go through and evaluate the integral, and you'll get 2 pi I out. If n is not 0, then you can find an antiderivative of this valid where it needs to be, such that over a simple closed contour we'll get 0 out for the integral. So give me some reasons on why those claims are valid. Antiderivatives can be used. You can't find an antiderivative when n equals 0 because that's where you need the logarithm stuff. And it's not defined on the whole contour, for example. But break it into two cases. We've done this, and probably in most of these cases already, when z sub 0 was 0 itself. But it's just straightforward computations. I know there's an integral of 1 over z in the notes somewhere. The grad problem has you consider a piecewise defined y of x function, x cubed sine pi over x for x between 0 and 1. Notice what happens at 0. We got a 0 in the denominator and a sine function, so we got problems there. And x equals 0 at 0, or when x is 0, the function, the y value is 0. And this is a dampened sine wave. And you're asked to show that that dampened sine wave has certain intercepts. Intercepts are easy. We've got an intercept here because y equals 0 at x equals 0, because that's the way the piecewise defined function is defined. And up here, that sine function is going to be 0 lots of times. And finding the intercepts, that's easy. That's straightforward. You're also asked, split up over an a and b part, to show that the contour z of x equals x plus iy. Okay, so it's a contour parameterized in terms of x, kind of like what we had over here, except over here they parameterized in terms of y. Anyhow, show this contour is continuous and it has a continuous derivative. That is, it's smooth. Because it's piecewise defined, you're going to have to deal with it in terms of one-sided limits. Limits as x approaches 0 from the positive side, and the sandwich theorem, or the squeeze theorem, whatever. You're familiar with that in terms of terminology. But you must use the sandwich theorem, and you must use one-sided limits on that graduate problem. And you should be pretty good to go with these hints.